Welcome to EDU World Space.
In this problem, we have a thin rectangular plate mounted on a vertical shaft here, and it's inclined at an angle theta from the axis of the shaft. We want to find the mass moments about the y and the z axes. Right? So if we take a look at the side view of this, we have our plate here that's at an angle theta. The length of the plate is A. It has a width of B. And what we're going to do is we're going to define a new coordinate system that runs up along the length of the plate. So inclined here. And I'm going to call that Z prime. Well, what we need to do is we need to find for the mass moment about the y-axis, we need to integrate the density times x squared plus z squared over the whole volume of this plate. Now, what we can do is we can, again, this is kind of an approximation, and we can split this, a volume element here, in terms of an area element times the thickness. Okay? So part of it is is the plate like this, or is the plate like this? And it's not really clear which way it is, but if it were thick, it would make a difference, obviously. But because it's thin, it's not going to make a difference. So we can use this V equals T dA. Right? So now we have an area integral. And we can figure out relationships between y and z and y and z prime. So z equals minus y tangent of theta. Okay? So that would define, this line here. Okay? And then z prime, we can see is y is z prime cosine of theta. So as we go up z prime, we go up y, but multiplied by the cosine of the angle here. All right? So we have that now. So what we need is a differential area element. Okay, so our differential area element is going to have, we want to break that up into a dz prime and dx, because that's how our plate is oriented. So a dz prime would be a little differential element like this, and then x would be a differential element in this direction. Or we can think about it as strips, because none of this is changing in the x direction. So a little differential strips up this. And so why we need to do this is because this is the dA is going to be dz prime dx. And so we need to get everything in terms of z prime. Now, to do that, we can substitute in, again, for the z here, we can substitute in minus y tangent of theta. So we get y squared tangent squared of theta. Tangent of theta squared. I forgot the squared in here. And then we're going to integrate from z prime, goes from 0 to a, and x goes from minus b over 2 to b over 2. Okay. Now, we need to convert, we want to convert z, we have this is a function of x and y, but we know the relationship between z prime and y. So dz prime from here, or dy equals dz prime cosine of theta. So dz prime is dy divided by cosine of theta. So fortunately, this isn't a polar integral, so theta is a constant. Otherwise, if we would have to integrate with respect to theta, that would be a really ugly mess. But fortunately, it's not, and so we can crank through these integrals, and what we get is rho over 12 TAB times b squared plus 4a squared sine squared theta. All right. So, and then we can volume of the plate is just A times B times T, and so this becomes, and again, depending on how that plate was, whether it was a squared off its thickness like this, or whether it was sheared like this might be an approximation. But if T is small, then it's okay. So we get m over 12 b squared plus 4a squared a sine squared of theta as the area mass moment about the y-axis. So we can think about some things here. What if theta goes to 0? It means that a drops out of here. A still shows up in here, but if theta was 0, then we would just have a plate about this axis here, and we can see that that would be an easy case, and we can just look that one up and see that we get the right answer. If theta is pi over 2, then we have a plate that's flat like this, and that's where we see that a squared has maximum importance. Obviously, so if we're trying to spin it about this axis and it's very, very long here, it's going to have a lot of inertia resisting spinning about the y-axis. So that makes sense. So that is about the y-axis. Now about the z-axis, we can go through the same process, but now we need to integrate rho x squared plus y squared. And again, take the differential volume element and assume that it's T dA. dA is again dz prime dx. And y, we can go back here, and y we have as z prime cosine of theta. So instead of changing this to dy, we're just going to substitute. We have y as a function of z prime, and now z prime goes from over here. We had to change here. This was going from 0 to z prime equals a. So in the y coordinate, it goes from 0 to a cosine of theta. So we had to transform our integration bounds here because we transformed over here. Now, in this case, we don't have to do that, so we just go from 0 to a. Z prime goes from 0 to a. X goes from minus b over 2 to b over 2. And again, we can crank through that integral and then use our volume and find it in terms of the mass, and we get m over 12 b squared plus 4a squared cosine squared theta. And so now we can see that in this case we have a cosine squared, in this case we have a sine squared, and that makes sense because about the z-axis, a is most important if theta is 0. So if this thing is vertical and we're trying to rotate it about this axis, it's going to have a lot of inertia as a gets larger and larger. And in that case, we can see here and then also if theta is pi over 2, and then it's basically flat and we're trying to rotate it around the y-axis, we wind up with b, or we're trying to rotate it about the z-axis, sorry, you wind up with b being a much more important factor because of this. We're trying to rotate about this axis, and then a comes into the picture through if theta is pi over 2, this is 0, but a still shows up because if we increase a, we're going to increase the mass.